Factoring polynomial functions and finding zeros of polynomial functions can be challenging. This lesson will explain a method for finding real zeros of a polynomial function. Please note that this lesson expects that students know how to divide a polynomial using synthetic division. You can watch our lessons on dividing polynomials using synthetic division if you need to brush up on your skills. Let's first state some definitions just in case you forgot some terms that will be used in this lesson. A zero of a polynomial function is a number that solves the equation f of x equals 0. These numbers are also sometimes referred to as roots or solutions. A rational zero is a rational number, which is a number that can be written as a fraction of two integers. An irrational zero is a number that is not rational, so it has an infinitely non-repeating decimal. The rational zeros theorem helps us find the rational zeros of a polynomial function. Once you find some of the rational zeros of a function, even just one, the other zeros can often be found through traditional factoring methods. In this function, the lead coefficient is 2. In this function, the constant term is 3. List the possible rational zeros of the following function. The constant term is -3. So all the factors of -3 are possible numerators for the rational zeros. The lead coefficient is 2. So all the factors of 2 are possible denominators for the rational zeros. All possible combinations of numerators and denominators are possible rational zeros of the function. The possible rational zeros are as follows: plus or minus 1, plus or minus 3, plus or minus 1/2, and plus or minus 3/2. Find the rational zeros for the following function. This is the same function from example 1. The rational zeros theorem showed that this function has many candidates for rational zeros. Therefore, we need to use some methods to determine the actual, if any, rational zeros. One good method is synthetic division. Let's try synthetic division. This method will let us know if a candidate is a rational zero. Let's show the possible rational zeros again for this function. There are 8 candidates for the rational zeros of this function. The number -1 is one of these candidates. To determine if -1 is a rational zero, we will use synthetic division. The synthetic division problem shows that we are determining if -1 is a zero. The first row of numbers shows the coefficients of the function. If -1 is a zero of the function, then we will get a remainder of 0. However, synthetic division reveals a remainder of 4. Therefore, -1 is not a rational zero. We could select another candidate from our list of possible rational zeros. However, let's use technology to help us. If we graph the function, we will be able to narrow the list of candidates. The graph of our function crosses the x-axis 3 times. It certainly looks like the graph crosses the x-axis at x equals 1. If you recall, the number 1 was also among our candidates for rational zeros. To determine if 1 is a rational zero, we will use synthetic division. The synthetic division problem shows that we are determining if 1 is a zero. Synthetic division reveals a remainder of 0. Therefore, 1 is a rational zero. In other words, x minus 1 is a factor of the polynomial function. Those numbers in the bottom row are coefficients of the polynomial expression that we would get after dividing the original function by x minus 1. We started with a polynomial function of degree 3, so this leftover polynomial expression is of degree 2. In other words, it is a quadratic expression. We can now rewrite the original function. First, let's show the factor x minus 1. Next, let's add the quadratic expression. X minus 1 times 2x squared plus 7x plus 3. We could continue to use synthetic division to find any other rational zeros. However, it might be easier to just factor the quadratic expression, which we can, as follows. 2x squared plus 7x plus 3 equals 2x plus 1 times x plus 3. Let's add back the factor x minus 1. Using the zero product property, we can see that our function has 2 more rational zeros, -1/2 and -3. 2x plus 1 equals 0, 2x equals -1, x equals -1 half. X plus 3 equals 0, x equals -3. Find the rational zeros of the following function. The only possible rational zeros are 1 and -1. Let's use synthetic division again. Both synthetic division problems reveal a remainder of -2. Therefore, neither 1 nor -1 is a rational zero. This function has no rational zeros. Let's look at the graph of this function. The graph clearly crosses the x-axis 4 times. Therefore, all the zeros of the function must be irrational zeros. The rational zeros theorem is a method for finding the zeros of a polynomial function. The theorem tells us all the possible rational zeros of a function. We showed the following image at the beginning of the lesson. P divided by Q is equal to the integer factors of a sub 0 divided by the integer factors of a sub n. The rational zeros of a polynomial function are in the form of P divided by Q. The term a subscript 0 is the constant term of the function, and the term a subscript n is the lead coefficient of the function. Using synthetic division and graphing in conjunction with this theorem will save us some time. The rational zeros theorem will not tell us all the possible zeros, such as irrational zeros, of some polynomial functions, but it is a good starting point.